All right, so today we're going to talk about two different things. We're going to talk about polynomial functions and we're going to talk about rational functions. Let's start off here with polynomial functions. And a polynomial function, this kind of looks like a pretty busy slide here, but let's just pick out some key things. A polynomial function, if you were to look in a textbook, this is kind of like the fancy equation that they would give you for a polynomial function. And what we're really looking at here, though, is just that it's going to have some sort of equation where this right here is going to be like a coefficient and your x is raised to a power. And then that power is going to decrease and decrease and decrease and decrease until it's down to just an x to the first power. And then the x will be gone. And these are just numbers here. Okay, so in the end, a polynomial function is just a nice, pretty, it's a cubic, it's a quartic, it's a polynomial. It's just kind of a nice flowy, goes up and down and up and down. There's no asymptotes, no breaks. That's a polynomial function. Nothing fancy going on. All right, now to understand how that's going to look, it actually has a very nice pattern to it. If you're n, and when we talk about the n, we're talking about the power, which ends up being the degree of this whole polynomial, whatever this highest power is. If that highest power is an odd, like for instance, a 3, then your graph is always going to look like this. If it's a 5, it just means that it's going to go down and back up. If it's a 7, it's going to go down and back up. And so it always ends up starting low and ending high. So when we look at this, we say that as x approaches infinity, the farther to the right you get, your y value is also going to approach infinity. As x approaches negative infinity, your y value is going to approach negative infinity. The only way that that's going to change is if your leading coefficient is negative. Then that would reflect and it would be the opposite. If you have a degree that is an even number, it's squared. Well, here's your classic squared. It's going to start high, come down, and end high. If it was to the fourth, it would just go down and back up. Sixth, down and back up. It's always going to end high. So these graphs, as x approaches infinity, your y is also approaching infinity. As x approaches negative infinity, y is approaching infinity. That would change if your leading coefficient was negative, then it would reflect, and those would both be negative infinity. Okay, so we kind of have to keep this in mind as we do polynomial functions of higher degrees, that odds start low, end high. Evens start high, end high. We also have something called the intermediate value theorem, and it kind of says that in a polynomial function, because there are no breaks in it, it's going to always have a value that falls. I mean, this is kind of the brief version. It's just saying that if you have an ordered pair here and an ordered pair here, you're always going to have a valid ordered pair somewhere in between there. Since there are no breaks in this graph, there's got to be a point that falls in between. Now we're going to use that concept to find 3 intervals of length 1 in which the polynomial is guaranteed to have a 0. And remember, a 0 means an x-intercept. So I'm looking at this, it's a cubic here, and I'm trying to figure out, without graphing it, where the zeros might fall on that. So we split up the work in class here, and everybody grabbed a value. This is an x value, and we plugged it in for x to see what we got back. And then we looked at these numbers. So I'm going to save you the trouble, and I'm just going to put in the numbers that we got. All right, so here's what we had. And then what we were supposed to do is figure out intervals of length 1, so a small interval where the polynomial would have a 0 or an x-intercept. So just looking at these, ultimately what we have here are a bunch of ordered pairs. This is an ordered pair. Plug in -3, you get -616. Plug in -2, you get -225. So what we're trying to do is figure out, okay, so where would this cross the x-axis? And we're looking here at these y values. If you were to think about it, -3, -616, my gosh, it's way, way, way down here. -2, -225, still way, way, way down here. -1, -42. But right here, when I got to 0, now my y value is 5. Something key just happened there. The y value went from being negative to being positive. And the only way that you can get from here to here is if you have a point in between, and specifically the point I'm looking for is that one right there. That would be an x-intercept. It'd have to have an x-intercept somewhere between this -1 and this 0 value. So when they said of intervals of length 1, that's what they're talking about. I don't know exactly where it's at, but I know it has to happen between -1 and 0. So then we would say, all right, then the zeros are between -1 and 0. Could you figure out where another one would happen? Okay, hopefully when you look at these y's, you're noticing, okay, but now we just went back negative again. So the only way to get back negative is to go back down and cross through that x-axis. So then it would be between 0 and 1. It would happen again. And if you keep looking down the line, where's the next time it's going to happen? We're below the x-axis. Now we're above it. So it would happen there. What you're looking for is it's switching, the y value switching signs. And you know that if your y value switches signs, then you have an x-intercept hiding in there somewhere. Okay, so on this next slide, we did a little graphing calculator lesson as far as using tables. Probably haven't used a table a whole bunch, I'm guessing. I don't typically do it a bunch in college algebra, but it would be kind of helpful in this scenario because we are specifically looking at intervals of length 1. So that makes your table a pretty good option. What you can do if you follow these directions, you can go figure out, or you can go look at an exact table. Instead of having on that previous slide, we just split up the work and everybody did value and figured out one answer. But if you're doing it on your own, you have a lot of these values to find. If you look at a table and you increment it, in this case, you increment it by ones, because that's what the directions want you to do, it works pretty slick. So what we did then is we just sat there and we looked at a table of values, and it just went all the way, well, we backed it way up to like a -20. So the x value was -20, and I'm going to look at a graph kind of here, not really look at a graph, but think through a graph from the table. All right, so way out here at -20, and then I was kind of just tracking it. And so I just jotted down here the places where something funky happened. So -20 was a positive value, which if you think about it, it's a quartic, that's even. It should be starting high, ending high. So if I'm at -20, yes, I should be up here somewhere. At -16, I was still positive, and you can see the kind of numbers we were dealing with here. I was still at a positive 8,280. But all of a sudden, at -15, it actually equaled 0. Now, that was a better scenario than I thought, because I'm just looking for where it switches from positive to negative. It actually equaled 0. So I actually found one of the zeros right there. It is exactly going to happen at this -15. So when I'm trying to find where they fall, I know exactly where one of them is. It's at -15. So I have one of the zeros here. That actually happened again later. I'm going to go ahead and point it out at a +24. So I have two of the zeros exactly. If you'll recall from college algebra, since this is a fourth degree, we should be looking for 4 zeros happening. And right there, I've got two of them. Okay, so let's think through what happened here. That was where two things that happened were funny. And then I saw right here that 18 to 19. So at 18, it was positive, but at 19, it was negative. So right there, somewhere way out here, x was 18 and was positive, but at 19, it was negative. So it crossed somewhere between 18 and 19. So I guess I'm just gonna start writing my answers. The zeros at negative 15, at 24, between 18 and 19, and I have one more I have to find. But try as we may, we did not find another place where that ended up switching from positive to negative, no more zeros exact. And so I didn't let anybody off the hook. It's like something's got to happen here. So we kind of debated, trying to figure out what's going on. I know that I have this 0 out here at negative 15. I have this 0 out here at 24, and somewhere between 18 and 19, there's a 0. But this is a quartic. It starts high, ends high. So there has to be another one in there. But they said there isn't one. Well, so we had to think a little bit about this, and eventually somebody comes up with it. But what you might notice here is that negative 16, it's positive. Then it hits at 0, but then it's back positive. The only way that can happen is if it came down and it bounced right there, and then it went positive. Instead of it cutting through and going negative, it actually bounced. And then on the next one, it actually did cut through, and then it cut through, and then this is what it looks like, start high, end high. So this one right here, because it stayed positive and then was positive again, that's actually what we would consider a bounce situation, and it would have a multiplicity of 2. Does some of this terminology ring a bell, I'm hoping? Multiplicity tells you how many times that is there. Multiplicity of 2. What that means is if you were to have that in factored form, which these are not factored, that means that you would have an x plus 15 as one of your factors, but it would be squared. All right, so all of that is to take us back to college algebra, if you'll remember the bounce cut packet. And so this is back to our toolkit of functions. We stopped at number 8, but now we're moving on, and you can put this in your notes or you can put it in your packet if you want them all in the same place. But what we're going to look at polynomial functions of higher degree. So far in our toolkit, the highest we went was a cubic. So now we're going to go farther. There's a lot of words here. I'm just going to highlight some key things. Polynomial functions are always continuous. They just flow up and down, up, down, up, down, beautifully, no breaks in them. All right. Your powers of x squared are always nice integers. The highest power will designate the degree, and we've talked about odd degree versus even degree, how that in behavior acts. Now, polynomial is kind of a generic term. A polynomial can be linear, it can be quadratic, it can be cubic. So we've already done a few, but now we're looking at higher degrees. So when in factored form, it's easy to identify the zeros because it's all factored and it's just sitting there. The power on each 0 indicates its multiplicity, how many times it is there. If you have an even power, it's always going to bounce at that spot. If you have an odd power on that factor, it's going to cut through the graph at that point, cut through the axis. To determine how to start your graph, you have to look at the degree. And again, we know that, and I have that written, here we go, even degrees will start high, end high. Odd degrees start low and end low. Okay, so a lot of words, a lot of talk. Let's go do it. Okay, so here we go. I'm giving you a polynomial function. It's already in factored form. That way it's going to be really easy to tell what the zeros are. So we're going to have a 0 right here, x to the 4th power. So that's going to have a 0 at 0. X plus 4 is going to get me a 0 at negative 4. Since it's to the 2nd power, that's an even, it's going to bounce at that spot. This is another 0. It's going to have a 0, and remember, zeros are x-intercepts, at 1. Since it's to the 1st power right here, it's going to cut. And then here we have a 0 at 3, and it's going to be a cubic. So that's going to make it be an odd, which means it's going to cut at this 3. Not only do I need to know where to put the zeros, I have to know what my end behavior is going to be. Your end behavior is all about if it ends up being an even or an odd as a whole polynomial. When it's all multiplied out, you look at the highest degree. When it's in factored form, you have to add up all of these because this is an x to the fourth. It's multiplied by an x squared, so now it's an x to the sixth, times an x to the first. Now we're at an x to the seventh power, and three more. Now it's an x to the 10th. So your end behavior is a y equals x to the 10th power. That's an even. So what that means is it's going to start high, it's going to end high, like a parabola. But there's going to have a bunch of stuff going on in between the start high and end high. But that's the idea. So I'm going to just go through. I'm going to find all my zeros and mark them. So the very first one was at 0. Even power, going to bounce. At -4, that one is squared. Even power, going to bounce. At 1, it's just to the first power. That's odd, going to cut. And 3, that's to the third power, and that would be an odd power, so then it's going to cut. And then I'm just going to start high, end high. Here we go. Come down. First thing I come across is a bounce. So it bounces there. Come back around. Got to bounce again. Oh, this time I'm going to cut. Come back up. Cut. Boom. Ends high like I wanted it to. These are nice because you can usually catch yourself if you goofed up because it doesn't end like you know it's supposed to end. That usually means you cut when you were supposed to bounce or something. Let's try again. Actually, this is one you're supposed to try on your own, but I guess I'm going to do it with you because I think they're fun. I can't stop myself. Okay, here we go. What's different on this one is that it has a coefficient here. It has a -3. Now, what that does is the same thing with every other function. This number in front is going to be a vertical stretch. But if you'll notice our y-axis is not scaled, and that's intentional because the numbers vary so drastically along your y-axis. You're going to have places where it's at a negative, really, really small, 0.3 or something, and then you have 7 million. It's crazy. We purposely don't worry about this. So I don't care about the 3. If it's, 7 million or 21 million, don't matter to me. But what does matter is that it's a negative. That does mean then I'm going to have to reflect this graph. So let's look at what our end behavior would be. We have an x to the third, so that's 3. Then there's 1 here, so that's 4. 3 more, that's a 7. So my end behavior is a y equals x to the 7th. That is an odd, so it should start low, bunch of stuff, end high. Except that it's going to reflect. So I'm going to do the opposite of that. I'm actually going to start high, end low. Let's get our zeros in here. I've got a 0 at 2. It is to the third power. That's an odd power, so it's a cut. At 5, odd power, going to cut. -3, odd power, going to cut. And remember, you're always looking at the power, not the 0 itself. I don't care that that's a 2. I'm looking at the power, the power, the power. That determines my bounce and cut. All right, let's see if we can do this. It's going to start high, end low because of the reflection. So it comes up here, cuts through, comes back, cuts through, boom, got it. Did what I wanted it to do. Now, ultimately, let me undo that. See if I can show you again. Not that I don't get super picky about this, but when you have something that is to the first power, typically it really truly just kind of cuts right on through. But if you have something that's cubed or higher, it typically kind of does this little wiggle through there. If you think of our parent graph on our cubic, remember how it goes and it sort of like swings through right there and kind of gets this curve action going? That's because it's an x cubed. It has a higher power. If it was an x to the first, then it's linear and it just like goes boom straight through. So just one more way you can kind of try to make this look a little bit more accurate. So this -3, well, really the only one that truly just cuts is this 5. The others should have some sort of a little shroom through there and then back up and go shroom. And if you make that noise, it'd be great too. And then that one just cuts through. All right, there you go. Let's keep moving. All right, so all of the previous stuff is stuff you have seen before, but what if it's not factored? Okay, that makes it a little harder for us. Well, guess what? You have to factor. So that's what we're going to do. We need to get it into the factored form so that you can see the zeros. I'm not actually going to graph these, but we're just going to talk through them. So first thing you want to do, looks like on this first one, we want to pull out an X. Okay, then you're going to factor the trinomial that is left. 2x and x, probably going to be a 5 and a 3. I'm looking to get my signs are going to be different, so I want them to subtract. I want the outer and the inner to subtract to a 7. So how about if we put a 5 there? That would get us a 10 and a 3 there. There you go. Those are going to subtract to 7. That's what I want. I want to have a negative 7, so my 10 needs to be negative. 3 is going to be a positive. Okay, so what I have are zeros at 0, -3/2, and 5. And since they all end up being to the first power, they would all be cut. And if they were, and as far as in behavior, since it's a cubic, overall it is a cubic, then we would start low, end high. That's just your classic wavy cubic right there. Okay, next one's a little trickier. Still a cubic. So still going to start low, end high, but the factoring is a little bit different. This is that factor by grouping because you got 4 terms there. So I don't like this to be a minus right here, so I change it to plus and negative, and I put in my parentheses. Pull out your GCF. So I'm going to pull out x squared. Over here, I'm going to pull out a -4. Look, they match x plus 3. That's what I want. So I put this x plus 3 over here. And then I do an x plus 2, x minus 2. All of a sudden, I'm thinking for a second that I changed this problem. So it might be different in your notes packet. In this case, it is just, again, it's just going to be a cut, 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 because they're all to the first power. I think the one I changed it to, it ended up having 2 of these that were the same. I was just trying to mix it up a little bit, because if I have 2 of them that are the same, then I would write that quantity squared, which means it would have bounced at that spot. So I think I tried to change it up a little bit. All right, time to move on. We're going to look at rationals now. And a rational is going to end up with an x in your denominator. So right here, you can see my polynomial function is way fancier. It's no longer polynomial. The numerator is the polynomial, but by putting in a denominator, I forced this into a rational. Now, anything in your numerator is still going to create zeros. But now, anything that creates a 0 in your denominator is going to be an asymptote. So let's go ahead and fill this in with those things. I've got a 3 that is an even power. That's going to be a bounce. I have a -1 even power. That's going to be a bounce. And at 5 odd power, that's a cut. Then I'm going to put asymptotes from anything that makes the denominator 0. So there's going to be an asymptote at 0. There's going to be an asymptote at 1 and an asymptote at -6. Now, how you react when you approach an asymptote is dependent on that power right there. And so if the power is odd, it'll do something. If the power is even, it'll do something else. Odd powers are going to be flips. Even power are going to be no flips. I'll show you what that means when we graph it. All right, the other thing I have to do before I get started is I have to know, oh, sorry, hang on a second. I'm going to go ahead and mark my asymptotes. So at 0, it's to an odd power. So this particular asymptote will flip. And then at 1, that quantity is to the first power, so it's a flip. But that -6 was squared, so that's a no flip. Okay, now let's talk about end behavior. This is a little bit different. You're still going to count up your x's, but you do it separately in your numerator and your denominator. So in my numerator, I've got 2 plus another 2 plus another 1. That's an x to the 5th. In the denominator, I have 1 plus another 1 plus 2 more. Okay, that's an x to the 4th. So in the end, if I had 5 x's on top and 4 on the bottom, those would reduce till I ended up with just a y equals x to the 1st. Now, what that means is it's going to look like a linear. It's going to start low, bunch of stuff, bunch of stuff, bunch of stuff, end high. That's what I want to do here. So I'm going to come over here to my graph, and I'm going to start down here low, and I'm going to come up, and the first thing I come across here is an asymptote. I cannot go up because I'm not allowed to touch that x-axis there, so it just kind of swings around and comes back down. Now, this graph is a no flip. What that means is if I'm going to approach this asymptote and get really close, headed downward, I'm going to stay down here when I pick it up again. I am not going to flip. I'm going to stay right here next to it and then come back up again. Okay, next thing I have is a bounce. Oops, so I got to come over here and bounce. Got it. And then it's going to approach this asymptote, so let's go back down. This asymptote is a flip. So if I'm headed way, way, way down, I'm going to flip and start way, way, way high. So it's here. Next thing is this asymptote. I don't get to cross. There's no 0 there, so turn it around. Come on back up. All right, it's another flip. So since I'm ending way, way high, I'm going to start way, way low. Come down here. I've got a bounce here, then a cut, and boom, I'm headed off like a linear. Okay, so you're combining the ideas here of both polynomials and rationals. All right, I have another one of these to try. All right, so I'm going to start with end behavior here. I've got let's see, x, counting up my x's here. It's a squared and a squared, and that's an x to the 6th. Got it. Oops, y equals x to the 6th over, let's count them up on the bottom. We got 1 here, 2 more, that's 3, 4, 5, 6, 7, and x to the 7th on the bottom. Okay, what's different about this example is that you have more x's on the bottom. So when you start reducing, you're going to end up at a 1 over x. Now that graph is in our toolkit, and that is called a rational graph or a reciprocal graph, and it looks like this. So what that means to me is that my end behavior is going to start underneath this axis right here. And it's going to be like approaching. I'm going to have this horizontal asymptote going right here. And it's going to be underneath here. And then I'm going to do a bunch of stuff, bunch of stuff, bunch of stuff. And somehow or the other, I have to end coming out on the top half or the top part of this and approaching my x-axis. That's how I start and end. A bunch of stuff in the middle. Let's go ahead and fill in our zeros from the numerator and our asymptotes from the denominator. Oh, looky there, I have a -3 to start with. Again, don't care about the 3, but the fact that it's negative is going to flip my graph. So the way that I start and finish will be reverse of what I just thought I was going to do. All right, let's put a 0 at 0. That x is squared, so that's going to be a bounce. Put a 0 at 2, another bounce. -3 is to the 1st power, that's a cut. And 6 is to the 1st power, that's a cut. Now let's look at our denominator and let's put in asymptotes. You'll have an asymptote at 1. That is to an odd power, that's a flip. -4. That is to an even power, so that is a no flip. 3 to an even power, no flip. And -5, even power, no flip. All right, got all the grunt work done. Let's go graph this thing. Remember that it's actually going to be the flip of this. So instead of starting underneath and going away like that, I'm actually going to start up above. And that means instead of ending above it, it's going to end below it when it gets reflected. So starting up here close to the x-axis, I'm right here. First thing I do is see an asymptote. I got to go up. This asymptote is a no flip, so that means I got to stay up here, come down. There's no x-intercept there, so turn it around. Again, it's a no flip, so I'm going to stay up here, come through. Oh, it's a cut. That cut actually came from a linear factor, so it's really just more of a cut through. And then what do we got? Okay, we got a bounce. So we got to come back up and we got to bounce. And then come back down. Now I have a flip. So that means if I end way low, I have to start the opposite, start way high, come through. This one actually touches. It's got a bounce going. So bounce there, come back up. Oops, I just caught myself. I stopped the video because I think something's not right. Actually, I should have shown it to you. Like I knew something wasn't right. I wasn't ending like I was supposed to. I missed putting in one of my zeros. Did you catch that? All right, that's coming from right here. And that's an odd, so that's a cut. Okay, so now I can finish. Again, you catch yourself every time, it feels like. So now I'm going to, this was a no flip asymptote. So since I ended way high, I'm going to start way high. And I'm going to come through. I knew I was supposed to end underneath because the graph was flipped. So that means I'm going to cut through right here, but this seems weird. Here's what I have to do. I can't go down. That's not in behavior. In behavior says go approach the axis. What happens is this gets a little bump in it and it comes back up and then it goes boom like that and goes approaches your axis. All right, there you go. Kind of fun stuff. All right, so I put this, I almost feel like this is maybe misplaced, and maybe in the video you're going to find that you already have done this in your notes packet. I don't know, I may rearrange it. This was just kind of a quickie, like, do you know what's going to happen in these different situations? And we've talked about a bunch of them. So let's talk about the easy ones first. If you have a y equals x, it's going to start low, bunch of stuff, end high. Going to look like that. X squared is going to start high, bunch of stuff, end high. A cubic, start low, bum, 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 bunch of stuff, and more of a cubic look than a linear look is how those vary. Okay, we did the 1 over x. If you have a 1 over x, you're going to have like underneath here, bunch of stuff, and then somehow or the other it's supposed to end up approaching again down there. All right, any odd will do that. So this odd will do that same thing. This comes down, approaches. Even though we have this in our toolkit, it's kind of a side note to the rational. If you have an even power on that denominator, instead of both of those two branches being in opposite corners like they are here, what happens is the squared forces everything positive. So this negative branch here actually pops up here and it kind of goes up. Some people look at that like a volcano looking thing. So both branches are upward on the even ones. Okay, again, a bunch of stuff in between, but that's how it ends. The constant, if you'll remember that from college algebra, I haven't done one of these, but this happens if you have the same number of x's on top that you do on bottom. Then they all cancel out and all you're left with is like a 1. Or if there was a coefficient on the front of it, you might have a 3 or a -3. What that ends up being is your end behavior is a constant, and you have like this, ultimately it's going to be like a horizontal asymptote, and your graph has to approach it. Now, whether it approaches from the top or the bottom is unknown. This was the thing, and bunch of stuff. Then in college algebra, that you had to do a test point. You had to put in a 10 out here to decide, am I above that asymptote or below? And then you had to put in a -10 to decide if you're above or below. It's not set in stone on that one. Now, that was kind of the hardest one that you did in college algebra. I'm actually going to bypass that, and I'm going to introduce you to a new concept, which is this one right here. This is not really as straightforward as just it ends like y equals x. This is actually going to follow what we call a slant asymptote. So what we're going to work on, which you didn't get a chance to do in college algebra, is finding not just vertical asymptotes, not just horizontal asymptotes, but now we're going to find slant asymptotes. You will do this every time your end behavior ends up being a y equals x. Okay, let's talk a little bit more about that slant asymptote. Now, slant asymptotes are going to occur when your behavior ends up being a linear. So that means you'd have one more x on the top than you do in the denominator. And to find the slant asymptote, you actually just do long division on that problem. And whatever your quotient is, there's your slant asymptote. Now, most of the time you're going to have some sort of a remainder. You just get to ignore that. So let's look at this example I've got here. This is a cubic over a quadratic. Now, a cubic over a quadratic would reduce to a y equals x. So I can tell that this is going to end up one of those ones with a slant asymptote. Now, this is not in factored form, so I would end up having to factor it. So let's go on to the next slide, and our goal is to not just find that slant asymptote, but try to graph this whole thing. All right, so the first thing, I've got this set up. I'll put it in division form here. And then we're going to do our long division on this. Hopefully you kind of remember how to do this. So you're going to look at this x squared right here, and you're going to say x squared times what gets me 2x cubed. And that would be 2x. Then you take your 2x here, and you're going to multiply it by these and write it down here. And then you draw a big line and you subtract. So let's do that. So 2x times x squared is 2x cubed. And then you have a 2x times a negative 3, and that's actually a negative 6x, which really needs to go over here underneath the 9x, because you do have to keep your like terms lined up. And that happens because right here in my divisor, I'm missing an x term. So when I come back and multiply, I'm missing a term here. So always line these up appropriately. So then I'm going to draw my line and subtract, which really to me just means I'm going to change all the signs. So this positive goes negative, this negative goes positive. And those cancel, and I have negative x squared plus 15x. And then I start all over. I come back here to this divisor and say x squared times what gets me negative x squared. And that would be times a negative 1. Take the negative 1 times the divisor, you get negative x squared plus, oops, notice here there's not a constant, so maybe a plus 0 there, because I really need to put this as a plus 3 over in there in that column, because I can't put it underneath the 15x. They're not like terms. Now I do my subtraction, which means you change this to a plus and change that to a minus. Those are going to cancel, and I'm left with a 15x minus 3. At the point where this power here is lower than the power here, that means you're done doing division. You've got your remainder right here, which I'm going to ignore. But this right here creates my slant asymptote. So I'm going to have a slant asymptote, and I'm going to write this down here. It's going to be a y equals 2x minus 1. And if I come over here to my graph, and I need to graph that slant asymptote the same way I do the other asymptotes. So the y-intercept is negative 1. And then I have a slope of 2, so rise 2, run 1. Get that in there a couple times, and then I'm going to dash this. Now, you still have to do all the other stuff. So what you do, you look at your denominator to determine where your vertical asymptotes might be. So now this doesn't come out super nice, but it's doable. Whatever makes the denominator equal to 0 means I'm going to have a vertical asymptote there. So if you can't do that in your head, and this one is not that nice, you can just kind of do a little side note. X squared minus 3 equals 0. Add the 3, square root both sides. So I actually am going to have a vertical asymptote at x equals, and don't forget when you square root, it's going to be a plus or minus square root of 3. Now that's not a very pretty vertical asymptote, but it's still doable. The square root of 3 is about a 1.7. So I'm just going to put this in here at a 1.7 and at a negative 1.7. All right. Last thing I got to work on is finding the zeros. So I'm going to take this right here, and factor that. So kind of squeezing this in everywhere. I'm sorry. All right, so I'm coming way over here now. And I've got I'm going to factor an x out for sure. Going to do that. Factor out an x. And then I get a 2x squared minus x plus 9. All right, so factors of 9 and 2 here that are going to somehow add up to a 1. I think I'm going to be in trouble because there's no way that I can get factors of a 9 and a 2 and have them add up to 1. They're going to definitely add up to more than that. So I think what happens here is this has to get solved with quadratic formula. The first part, I know that I'm going to have a 0 at 0. That's good. I know that because I factored out the GCF. But what's left is this quadratic. And if I do negative b plus or minus square root b squared minus 4ac all over 2a. And then inside my radical here, I have a 1 minus, that's 8, 9, that's 72. 1 minus 72. Okay. Unfortunately, that's going to be imaginary. Now, I could keep going, but I'm just going to make a note here that this is going to be imaginary. If you have an imaginary root, remember what that would mean graphically? It means that it's not going to create any real solutions. So there are no real x-intercepts beyond the one that I got right here from factoring out the GCF. So my graph should not cross the x-axis ever again on that. So over here, I'm writing the zeros would be at 0. That's the only 0 I have. All right, so now it's time to graph. When we graph, you have to be approaching this slant asymptote. So it's sort of like we do with the horizontal asymptotes, where you have to decide, should I start above this asymptote down here, or should I start below it here? We don't know which side to start on. Either way, I'm kind of approaching 0. So what I would do is, let's think through this. If I put it here, I'm going to kind of pull away and start going up and approaching your vertical asymptote. The problem with that is that I just crossed the x-axis right there. And I can't cross the x-axis. I don't have a 0. So that tells me I'm going to have to do this thing where I come from the bottom part here. Come up here, and then it turns around and it goes back down and approaches. All right, now that particular vertical asymptote, remember that came from this right here, and those were each there once, so they are both going to be flips because the power is 1. So if it's a flip, that means I got to come way up top here. Since I ended way low, I come up top. The next thing I'm going to come across is this x-intercept. So it's going to swoop through right there and keep on going. Now, I know some of you are freaking out because I just crossed that slant asymptote. But here's the deal, is that we don't ever cross vertical asymptotes, but we can cross horizontal asymptotes and we can cross slant asymptotes. All they indicate is that I'm approaching something. The vertical asymptotes imply that something is undefined there. That's a different deal. So totally okay to cross that. And then I come across another flip. So I come up here and got to turn it around and go approach my slant asymptote. And that's my end behavior right there. Okay, so that process right there, it's very similar to that. This one was a little bit of a higher power because we were dealing with a cubic. So you had a little bit more going on in this graph than sometimes we have, though you do always have to find this information out. And then you have to make this decision on which side of this to start on. If my 0 that I had was actually here, then I'd want to go this route with it. So it can vary. All right, so hopefully that gets you a good start. Good luck.